Hello, wonderful people of the internet. Welcome back to another episode of Leos Labs. Nick, Shadowmacia, hey, thanks for coming in. And anyone else who might be lurking in chat, hey, thanks for being here. So today, we're actually going to hop into Algorithm Archive PRs and work on that for the most part today. I do want to go through the chapter on the chapter that was just recently put up on the physics. What is it? It's like a Monte Carlo physics thing. I don't remember what it was. I should remember it. But we'll try to get that one in, or at least reviewed today, and that's going to be the primary focus on today's stream. I didn't stream yesterday or the day before, or technically the day before that. It's been like 3 days since my last stream. Let me acknowledge and explain what's happening, and why it took so long, and just kind of explain what's been going on. I mean, look, you guys know what's been going on. My mental state has been like, kind of all over the place for the past, 2 years? So, like, I don't think I need to be like too, like, I don't need to explain it too much, but one second, I'm flipping around so many desktops. But the fact is, I basically tried to stream 3 days ago. I tried to push through it and just kind of like make a stream, but I started streaming and I started talking, and then I opened up YouTube for a second and I saw a video from Reducible, right? And this video from Reducible had a very similar thumbnail to some of the content that I put out previously, Reducible has a habit of making videos about things that I've done, and more than that, what's super frustrating is I have actually reached out to him about it, and again, I'm not going to sit here and say that I'm not going to smack talk him or anything like that, but basically, I asked if he'd be willing to collaborate with me in the future, and what he said is, do you mind if I cover an algorithm you've already covered, but in a better way? And I'm like, dude, like, I mean, that's fine, I guess, but like, could you not like be so like, there was just something about the way that it was said that made it seem like, he wasn't even acknowledging the amount of work that goes into each of my videos, right? It was like, I don't know what it was. There was something about the way that it was said that really just rubbed me the wrong way. And this is true for a lot of content creators. I talk to them, and the fact is most people don't understand the type of content that I make on YouTube. I get it, to some extent it's, I don't know, it's frustrating, right? And so when that happened, I just kind of got in my head and I had to leave. And I hate it. I hate that every single time I open YouTube as a platform, I just get really pissed off and like, I've mentioned this many times before. So here's what I'm going to do, guys. For the next 5-10 minutes, I'm going to do what will be, I promise, my very last rant about YouTube ever on this channel. So if you have heard this all before, I understand. I totally and completely understand. Just leave. Come back in 15 minutes. I get that I've talked about this, so many times, and it's really just not worth talking about anymore. So that's why this is going to be my very last YouTube rant. I'm going to clip it. I'm going to put it on my side channel. So if anyone ever talks about YouTube here on this Twitch stream again, or like we start talking about the type of content that I make in a way that starts to get ranty, what's going to happen is I'm just going to say, screw it. We've already talked about this. And, here's where we talked about it. And that way I don't have to, keep going down this rabbit hole of just like, like cycling down this, whatever YouTube toilet bowl. I don't know. You know what I'm saying though? Like, the platform is very disheartening. It's always been disheartening, as opposed to Twitch, which is always relatively uplifting. YouTube is pretty much always just degrading. And it's super frustrating because, the content that I make is different than the content other people make, and it serves a different purpose, right? YouTube is upsetting, yeah. Okay, so let's just talk about it. Here's what's going to happen. Throughout the past 3 days, I spent all of my time doing nothing but reading papers, and it was honestly the most enjoyable experience I've had in like 3 years. I was just reading papers about a topic that I didn't know so much about. And let me just explain to you, like, how much enjoyment I got out of this. It was insane. Like, it was genuinely, for the first time in like years, I felt like, man, this is what I want to do, I've come up with a short rant about modern incremental games. Feel free to put it in the chat. This will be the rant section. We'll all just rant a little bit, right? So I'm going to draw a little graph here. And I'm just going to kind of, I don't know, like maybe a rectangle is fine. I'll put it in pink. Why not? Okay. So this is the amount of enjoyment I get from papers. All right. Papers, right? And just to put some other things on the board, let's say this is the amount of enjoyment I get from working out. So this is particularly swimming. I actually get a lot of enjoyment out of swimming. So swimming is going to be here, swimming, which is to me the most fun part of working out. So swimming. All right. To put something else on the board, let's go ahead and put down video games. So, a long time ago, I used to really like video games. Like during high school, it was something that I did all the time. I loved it. All the time. I also have a rant about modern software development education. Oh, dude, let's just have this. This is the rant moment. Everyone just rants about something. We'll read through all of it. That's just what we'll do. So for me, video games are no, that's too high. Video games are like way down here. Like it's barely even a metric. So we'll say video games here. A long time ago, I used to really, really love video games, but recently it's just frustrating is what it is. Like every time I play a game, I just get pissed off and I end up feeling like I wasted my time. Now, reading books is only slightly higher than video games for the similar reason. It just, if I want to read something, I don't want to read books. I want to read papers, And so now let me just go ahead and draw where YouTube is. YouTube is only marginally, if even, above video games. For me, in terms of actual enjoyment as a viewer, right? Not as a content creator, as a viewer, as someone who goes and watches YouTube, right? I don't find very much enjoyment in it. And, just for the record, I'm actually probably comparing, probably the best YouTube video channel, the best channels on YouTube. So we're talking about Smarter Every Day. We're talking about, Mark Rober. We're talking about, Three Blue and Brown. The best YouTube creators, at best, are about 10%. The best YouTube creators will make me about 10% as happy as reading an average research paper. Like, it's just so, it's just so incredible how much more I enjoy this as opposed to this, right? And that idea, it just permeates through my YouTube content, and we'll talk about that in just a second. So Incremental Mass is literally just a ripoff of other games, which aren't even that decent. Basically, there's a guy that makes incremental games. He has two specific games I want to talk about: Incremental Mass and A Balanced Upgrade. The Balanced Upgrade is a game with a crappy design, but actually decent mechanics and a base for the game. And Incremental Mass gets much more attention. What the heck? The game is literally just buy this upgrade that boosts things, repeat. That sounds kind of annoying is what it is. Okay, so now look, here's the thing. I've actually been thinking about this a lot, the type of content that I create and why I actually genuinely like reading papers more than any other type of content. And I think it's because there's such a high information density in academic papers that you don't find anywhere else. When you read a paper, you're guaranteed to learn something new. Whether that be an amazing new thing that really fundamentally changes how you look at things or not, there will be something new in that paper. And it's just amazing. I really, really love the fact that you can just pull up a piece of paper, take a look at it for 5 minutes, and there's something new. Meanwhile, with YouTube videos, you're going to spend 20 minutes staring at a screen and getting absolutely nothing from it. Even if, they'll clickbait you for like 1 minute of content. It's like, hey, here's a video about X, but they only talk about X for like 30 seconds in the middle of a 20-minute video. It's just a waste of time. More than that, YouTube videos are just incredibly slow. It's like, if you have to watch them at 2, sometimes 4 times speed to get anything out of them. It's just so frustrating, The base concept of the balanced upgrade allows you to play around. I hate this. This is the end of the rant. Be right back. See ya. So basically, at my university, the computer science classes is literally not preparing students. They don't take any architectural classes, so they don't understand any of the big picture. I work in software engineering, and the sheer lack of preparation that students have coming out of the university is appalling. Whoa, wait. I 100% agree with this. Not only for like software engineering, but like towards any field that requires computation. I feel like university improperly educates people towards that field. Pretty much everything relies on software nowadays. And like the number of scientists who don't understand how to write basic Python code is ridiculous. I read a study the other day that 10, 20%, oh, not 10, some high percentage of students coming out of university can't even do like a FizzBuzz exercise coming out. It's absolutely ridiculous how little it actually prepares you for the workforce. I guess I go to these classes and discuss it with my friends who graduated, and it's not just them. It's crazy. Yeah, like I'm 100% with you there. It's super frustrating. Like for me in particular, I work with people who have to work on high performance computers all the time. And the number of times I've had to teach people how to copy data from the cluster to their own local machine is insane. There's so many little things that you should just know. Like, how do you not know this if you've graduated from university, And look, I realize that I'm privileged. I'm coming from a university in the US. Not everyone had the same education as I did, blah, blah, blah. But You know, like my university was from Alabama, not like the best university in the US. You'd expect, you know, an international community to at least have some standards, you know? Anyway, this is neither here nor there. So with the papers and everything else, let me just go to my YouTube channel right now, youtube.com here, and let me just go to my channel here. Okay, shut up. And let me just go to my videos. So again, for me, the ideal form of content is a very short form, very curated piece of work that provides the maximum amount of information in the minimum amount of time. That's what I like. And so all of my videos are more or less tailored for this type of conversation. What is the eigenvectors? 4 minutes. Monte Carlo, 3 minutes. Determinant, 3 minute. Impossible lenses, 3 minutes. I only have like 1 or 2 videos over 5 minutes. And I think one of them is a split operator method. The other one's Gaussian elimination. And then problem with software engineering and flood fill. The reason these are longer is because they were literally clips from my Twitch stream, and I didn't like that. This one is longer because I tried to make it longer. This one's longer, again, because I tried to make it longer. But for me, like, the ideal content on YouTube is like, you know, 1-2 minutes or less. You know, I don't like long form content. You know, live streams are different because at least with live streams, there's a conversation between you and the content creator. But like, I don't know, for me, I just cannot stand, you know, any video over 10 minutes. I just can't watch it. I don't have the attention span for that type of thing. You know, if you give me a video, I will definitely watch the video. I'm sorry, other way around. If you give me a video, I won't watch it. If you give me a research paper, I will read it, and I will probably like it. I can't think of a single research paper I've ever been given that I haven't enjoyed to some extent. Meanwhile, I can only think of maybe 1 or 2 YouTube videos that I've watched and I've actually enjoyed enough to keep going. Like, you know, like I've watched the video and I was like, wow, that was something I really want to learn more about, you know, or this is something that's rather inspiring, right? Now, there's a bunch of content creators out there that have all given me some information that have allowed me to like learn something afterwards. So 12 Tone, for example, taught me about 4D, musical spaces. I thought that was really interesting. Lots of stuff with 3 Blue and Brown. Again, he'll hit something and then I have to look it up after. Same with Smarter Every Day. Basically, they all give me some little nuggets of information and then I'm like, okay, great. And then after that, I end up, you know, taking time to learn it afterwards, which is fine. Like, that's how all lectures work. It's totally okay. But what gets me is that I know that my content is not tailored for YouTube. I know there are 2 reasons why it's not tailored for YouTube. One is that, you know, it's a huge pain for one. I ask people to leave the YouTube platform. Like at the end of every one of my videos, I'm like, yo, you know, go to the algorithm archive. So that's one reason it's not tailored for YouTube. But the other reason it's not tailored for YouTube is that I assume people have information before clicking on the content. And the reason I do this is so that I don't have to spend, you know, 5-10 minutes talking about background information. And so whenever I talk to people about this, they're like, why don't you spend 5 to 10 minutes talking about background information and then give them the actual information? It's like, the reason I don't do that is because I fundamentally hate videos that do that. It's such a waste of my time. And then I find myself constantly pressing the right button again and again and again and again for the chance. Like, you know, the small, slim chance that there's actually going to be information in the video that I didn't know before. And it's just so frustrating. At least, you know, with papers, I can guarantee something new. With videos, I can't. You know, and so this is my problem, right? So I gave it a lot of thought. Hey, Amaris, by the way, how are you? I gave it a lot of thought as to what to do. I could stop making these types of videos. I could start making videos that are a bit longer form, that, you know, are more in line with traditional YouTube content, with the hope of just getting more people in the community, more people involved. This would mean that my YouTube channel would be fundamentally for different people. It would not be for people like me who want short videos. It would be for people who are on YouTube anyway, and they're browsing and stuff like that. And this is fine, right? Like, I could do that. And it's fine because, like, you know, the point of YouTube is more or less an advertisement for the rest of the platform. And so for me, I don't mind, you know, having one part of the platform that I don't like. But I was thinking about it more and more over the past few days, and I'm just really not content. I don't like the idea of making content to put on this website that I don't find enjoyable to some extent. You know, I mean, there's some of these videos that are actually quite good. All the way back here, Impossible Lenses, that was a research paper. Color quantization came from us doing galaxy simulations. Gift wrapping algorithm, again, I combined like 4 papers into one 3-minute video. Word sort, again, was similar. Then we have how to make fractals by counting, which is, again, one of those things. The fractal for an algorithm, proximate counting. There are a whole bunch of videos in here where, like, I genuinely think are some of the best content that YouTube has. And I know I'm super biased here, but like, I genuinely think like the idea that was presented in these videos is super good. Now, look, I'm not going to say the implementation was good, but I'm going to say that, this is stuff that I think I probably would enjoy watching, So what I think I'm going to do from now on, obviously I said I'm not going to rant about YouTube anymore on Twitch. This is the last time I'm ever going to rant about YouTube on Twitch. I promise, never again. Here's what I'm going to do. I'm going to make sure that every single video I put out on my main channel is fundamentally new. I know I said that a few times before, but I also kind of, toyed with the fact that maybe I can make more conversational videos or something like that. No. I'm going to make it so every single one of my videos is new. And the reason I want to do that is because I'm really going to try to make videos that both appease people like me, who really do want new things that they've never seen before, and also appease the masses, people who are just interested in like normal YouTube content, right? And I figured the only way to do that is just to do things that are new, literally just break my back, try to get new stuff out, and just show people why this is interesting. I think it's really important to continue publishing research papers, to continue with the algorithm archive content, because that's where like the actual interesting stuff happens. But I think it's also important to have YouTube videos that like reflect, I basically had two options. My one option was to go the easy way and just to, make content that I don't really like, but I know other people are going to like, or do the hard thing and try to make content that I like and other people like. And I'm just going to try to do the hard route for the next year. It's probably not going to work out. We're going to see how it goes. Probably it's going to be the same thing that has been happening where I get 6.6K views after 3 months of a video that I genuinely thought was super good. Like all of this stuff I thought was really good. Now, look, it could have been better. And, I know how to make the future content better, but like, it's just, I don't know. I just get frustrated. Every single time I open up YouTube as a platform, I get frustrated. And I think it's just because I don't understand YouTube. I don't understand how this type of content is what people like. It just doesn't make sense to me, Anyway, I'm going to go ahead and do some algorithm archive reviews. It's not going to be a super long stream today. I'm really sorry. I'm just still super down. I know I burnt myself out, and I don't know how. It was just like talking about YouTube and thinking about it just makes me really pissed off and angry. So what I'm actually going to do is I'm going to take a look at the Metropolis algorithm and Python implementation. I'm going to read through it, and we're just going to see how this goes. And that's the point. So that's all we're doing on today's stream. If it's not particularly engaging, I'm sorry, but this is what we're going to do. So yeah, we're going to hop into it. Okay, so the first thing I'm going to do is pull it down locally and just build it and see what we can do. So command line instructions, and then we're going to grab this guy and bring it down locally. I'm good. I'm playing Return of the Obra Dinn, and it's really good, if a little traumatizing. Right. Very excited for chapter review. Yeah, we really need to get this done. So cd into projects, algorithm archive, git branch, git checkout master, git pull upstream master. Okay, and let's just paste this guy. Dang it, I screwed up. Okay, let's try it again. Okay. Let's go here, paste this. Okay. Good. Sure. Over here, we're going to cd into projects, algorithm archive, and then we're going to run npm run serve. And we'll just hop through it, see what we need to do. I'll probably have the chapter up on one side, and then I'll have the PR up on the other side. So I have them both up at the same time. Which means I need to open up a new browser. Let's go here, move this up here, this down here. Okay, and let's go to localhost. And there should be a Metropolis Hastings somewhere in here, probably at the bottom, I would imagine. No, wait, where was it? There it is, Metropolis in there. Sure. Okay. Let me zoom in. Oh, is that zooming out? Zoom in, and let's just read through it. And then the other thing I'm going to do is have the PR up over here. In fact, let me modify this. So this is actually going to be over here. 1 second. That should do. And now this is going to be over here. Okay, move this over there. And scroll up. And now we're going to do files changed. Okay, and we'll just kind of knock this out. It's fine to add the IPython checkpoints or whatever. I really don't use IPython, but maybe other people do, so I think it's fine. So the Monte Carlo integration method, here we are, uses random numbers to approximate the area of pretty much any shape we choose. The Metropolis algorithm is a slightly more advanced Monte Carlo method, which uses random numbers to approximate a probability distribution. What's really powerful about this approach is that you don't need to know the probability function itself. You just need a function which is proportional to it. Now, we have not talked about probability density functions before, which is fine. It's not a big deal. Oh, this is gonna be a pain. Okay, here's what I'm gonna do. I'm just gonna have that's gonna be a huge pain. Okay, we're gonna have to flip between the two of them. Let's go here, move this over here, and then go to localhost. Okay, Metropolis again over here. I do think probably it makes sense to be under Monte Carlo. Let's just go to the summary.md, which should be somewhere here. And what I'm going to ask is that we change this to be 4 spaces forward. Okay, here. And okay, start review. Yeah, I should mention what this is going to do. Edit here, and we're going to say this. 1 second. Monte Carlo. Let's see, best idea. So honestly, Monte Carlo methods in physics are like, there's just a bunch of like things to talk about with Monte Carlo methods in physics. So, presumably we should have like a Monte Carlo like section. We should, let's see, like physics. All right, let's update that comment and see what we have. Hey, Adelix, how are you? I hope you're having a great day. Yeah, I'm okay. Okay, let's go here, Metropolis. Okay, let me scroll in. I'm using Arch Linux with the OpenBox Windows Manager. So OpenBox is what you actually need to know. Okay, so Monte Carlo integration method uses random numbers to approximate the area of pretty much any shape we choose. The Metropolis algorithm is a slightly more advanced Monte Carlo method, which uses numbers to approximate a probability distribution. Right. Arch Linux or Ubuntu, select one and reason. Well, I mean, I just use Arch. It's to me easier to understand than Ubuntu. Back in junior high, I installed Linux for the first time. Arch was my first distribution. It just clicks with me in a way that, Ubuntu doesn't. In particular, the package management on Arch is just way easier than the package management on Ubuntu. At least for me, Pacman is just easier than apt-get. So for me in particular, Arch clicked with me in a way that Ubuntu doesn't. But I do know that if you're into having a fancy GUI, then feel free to use Ubuntu. Ubuntu's GUI is probably way better than Arch's GUI. I mean, they have basically the same, but Arch's is Pacman, and Ubuntu's is apt-get. So, okay. What's really powerful about this approach is you don't need to know the probability function itself. You just need a function which is proportional to it. Why is this helpful? Well, we often have probability functions of the following form. F of x, integration of f of dx, where d is a domain of p of x, i.e. all possible values of the coordinate x for px is defined. We must talk about probability distribution somewhere else. Yeah, I don't. Do we use? How could we not have talked about probability distributions anywhere else? We must have. I think we talked about it when we talked about the split operator method. Let me see what we said about that. I mean, surely we talked about it with data compression as well. Let me go here. Split operator method should be there. There. Maybe I didn't really talk about it too much. I don't love Pac-Man because I don't use it yet. So yeah, if dev doesn't rewrite the balanced upgrade, I adopt this concept and may make this into a decent game. All right, so you're going to do some game development? Yeah, so okay, right. So for those of you guys who don't know, I'm sorry I'm so scattered, by the way. For those of you guys who don't know, I'm currently working on the Arcane Algorithm Archive. It's an online textbook with a bunch of different algorithms in it. We focus on algorithm quality as opposed to algorithm breadth, if that makes sense. So instead of having a lot of algorithms, we focus on, providing a good description of each algorithm. The idea is that it is a textbook that you could print and you could learn a lot from. And so, for example, you could go to the Euclidean algorithm here, and you can basically switch between all the different languages that we have available. And so the algorithm that we're reviewing right now is for the Metropolis Hastings algorithm. Yes, good. I will call it, took inspiration from, when in reality I'll just steal it. Oh, I see. I guess. It's often easy for us to know f of x. But the integral in the denominator can be quite difficult to calculate, even numerically. This is especially true when the coordinates x are multidimensional. The coordinates x are multidimensional, and f of x is an expensive calculation. One example use case is a multidimensional physical system with energy E, for which we know that f of x is e to the negative e of x, but p of x is almost always impossible to calculate. Okay, I need to think about this again. It's been a long time since I did any Metropolis algorithms. So I actually don't know what they're talking about here. Look, I took a dip away from physics a long time ago, and I honestly have completely forgotten most of the stuff because it's not worth remembering. So as you can see from me forgetting how Taylor series worked the other day. Let me reread through this. The Monte Carlo integration method uses random numbers to approximate the area of pretty much any shape we choose. The Metropolis algorithm is a slightly more advanced Monte Carlo method, which uses random numbers to approximate a probability distribution. What's really powerful about this approach is that you don't need to know the probability function itself. You just need a function which is proportional to it. Why is this helpful? Well, we often have probability functions of the following form. P is equal to f integral over some domain of f of x dx, where d is the domain of p of x, i.e. all possible values of the coordinates of x, for which p is defined. Is that true? The probability distribution for every point f is going to be the probability of finding that point within a domain. Okay, so I'm gonna just try to reason this out really quick. Let me go to the text here and say, I think it might be nice to say something as well. So something like, this means intuitively, this means that the probability of finding x, let's see, the probability of finding like a point at location x is related to the probability of finding it at any other point in the domain. So what I'm trying to say is the following, right? Like if you have journal new page before, like, so if you have a function that looks something like this, I guess here, right? This is going to be your probability density function. And the idea here is that you're most likely to find it here, and you're very unlikely to find it here. So I'm trying to find like an intuitive way to describe that. So intuitively, this means that the probability of finding a point at location x is this is why I always like the integral of the probability distribution over all space is equal to 1 or something like that. Because this provides a clear point here. It's like, hey, you only have one particle. You're likely to find it here at this point in the domain. So let me see, what do we have here? Is that actually what this is saying though? So we have the integral over the entire domain of f of x of dx. Okay, yeah, okay, that's true. So you're integrating over all of the domain f of x of dx. So what is f of x in this case? It's often easier for us to know f of x, but the integral in the denominator can be quite difficult to calculate even numerically. This is especially true when the coordinates of x are multidimensional, and f of x is an expensive calculation. One example use case is a multidimensional system with energy E of x, for which we know that f of x is equal to e to the negative e of x. But p is almost always impossible to calculate. Okay, so I'm actually lost here, and I'm just going to explain why I'm lost. Intuitively, probability of finding it the rest of the domain, but that's not exactly what this is, because the integral. Okay, I'm just going to write down what I'm thinking here to say, okay, bear with me. I do have a PhD in physics, but it's been a super long time. This algorithm bear with me, I do have a PhD in physics, but it's been a super long time since I did any physics. It seems that he's just saying it's hard to solve this function sometimes, and here's an example of that. Right, I get that, but I guess I'm going to try to explain why I'm lost here. So I think it'd be nice. Add some context. My understanding. I actually don't know what the integral of x is. So how does that make sense? So let's say you have f of x. So here's f of x, journal, new major 4. So we have some sort of function of x, which is f of x is going to be equal to sine of x, right? And so what they're saying is f of x over the integral of sine of x dx is going to be equal to, over the domain, is going to be equal to p of x, right? So that's what they're saying. So all this is doing is it's scaling. It's scaling your function. So here's your function, right? And let's say the integral of all this is 3. So all you're doing is you're scaling your function by 3, and you're saying your probability distribution is like the sum of everything put together is 3. So in some sense, you could say, that's the amount of stuff you have. And then you're dividing your function by 3, so you're just squishing it down. And this is kind of a normalization procedure in a way, I think. So it would be nice to add some context to this line. My understanding is that the integral denominator x as a scale order to find the actual probability. So like usually intuitively I would add right. So I usually intuitively add the integral of psi star psi is like roughly, how many particles you have at this location. Let me see if I can read this a bit better. So we have p of x is your probability distribution of essentially finding a particle, right? Of a particle location. Hey, how are you, Shadipto? We're going through the chapter. It's going to be, like, again, I'm going to ask some really dumb questions here, and I'm just going to put them in the review. In some sense, I don't really like doing the reviews on stream. This is a problem that I used to have before, because I'm fine doing code review on stream, but the issue is with the chapter reviews, I get kind of sometimes I'm a bit mean, and I don't mean to be mean. Like I'll say something like, I don't understand this, and then it takes me a second, and then I'm like, I understand this, right? So if I say something, it could be me being bad, or it could be the chapter is just not being clear enough, right? And making a distinction between the two of them is difficult sometimes, right? And so usually it's not until I get through the whole chapter and I figure it out. So we're at the first bit of the chapter right now, just for this. And notationally, this is totally fair. Like, this is totally fair. I've seen this notation before. But we haven't actually talked about probability distributions too much outside of maybe the split operator method. And so what I'm trying to do is give like kind of some sort of description of what this means physically, right? I mean, I get that, you're basically taking some sort of function and you're scaling it by the integral of the function over some domain. I get that. But like, how exactly does that provide a probability distribution is what I'm trying to like put into words. And I don't have that right now. I'm trying to think about that intuition. And the other thing to point out here is like, yeah, I mean, I did Metropolis Hastings. Wait, is this Metropolis? Is Metropolis the same as Metropolis Hastings? Maybe I've never done Metropolis. Maybe I've only done, I think they're the same, right? Yeah, okay, it's the same, I think. Yeah, okay. Yeah, so this is where we're at. I'm just going to go through it. Okay, so Hastings has an asymmetric g of x. Oh, okay, interesting. Right, okay. Then I maybe never did the Metropolis algorithm. Maybe I only did Metropolis Hastings. But anyway, the point is, I did it like 10 years ago. Like, it's been a long time. Yeah, it's been about 10 years. It was one of the first classes I took in university. And so like freshman year of university. So like literally right out of high school, I did this. So it's been a long time. And I didn't really use it during my PhD. So I've kind of completely forgotten how this method works. So I'm going to say some really dumb things here, and you're just going to have to, I'm sorry about that. I'm going to say some really stupid things. Okay, so let's go here. Right, so when I think of probability distributions, what I normally think of is, the integral of psi star psi is going to be equal to the number of particles you have, right? Like, that's what I normally think of when I think of particles here. How exactly dividing your f of x by the integral over a domain. All right, again, just asking stupid questions here, and we're gonna go for it. I naively think p of x in my mind is related to the probability of finding a particle. For example, so what is f of x? So if f of x is sine of x, right? And you scale that by, the integral of sine of x over some domain, how does that give you a probability distribution? I guess is my stupid question. And feel free to answer in the chat as well. All right, again, we're going to slowly but surely get through this. And I think you being here in chat is going to help. So if I say something dumb, just like explain it, then, that helps me provide better critique. Okay, so it's often easy to know f of x, but the integral in the denominator can be quite difficult to calculate, even numerically. This is especially true when the coordinates x are multidimensional, and f of x is an expensive calculation. So one example use case is a multidimensional physical system. Sure. With energy of E of x, for which we know that f of x is equal to E raised to the negative E of x, but P of x is almost always impossible to calculate. And it is impossible to calculate because we don't know the bounds of the domain, or we don't know what E is. Which, anyway, it doesn't matter. So the two issues I have with this paragraph, well, I realize it's a physical algorithm here. But yeah, I think providing some example would be quite nice. I'm using Arch Linux. E of x is difficult to integrate. And why is that? Now, look, I did imaginary time evolution and stuff like that, but it's been a long time since I did these calculations with E. So I'm trying to remember why is E hard to calculate? E is hard to calculate because usually you calculate E by having some sort of Hamiltonian h, and the Hamiltonian h must be usually time evolved or something like that. So yeah, there is a potential that, yeah, okay, I see this. Yeah. So could we provide like, and again, I'm going to erase this comment because it's probably done later. Even if E is easy to integrate, F may be hard to integrate. Right, that's fair. That's totally fair. Anyway, I'm going to keep going, and like I'm going to erase some of these review comments as I go through. Again, usually the way I do reviews is I just kind of write whatever I'm thinking as I go through, and then I erase the unrelevant comments and stuff like that as we go through. Okay, so let's keep going. For the record, I mean, you've got some good visuals in here, and just zooming through it, it seemed fine. There was the comment about not using NumPy, but I'm going to be honest, use NumPy. Like I don't know anyone specifically in the area of physics who uses Python without NumPy. It's super rare. So the Metropolis algorithm is very similar to random walk. So let's see how we can get a distribution from a random walk. The dot in the figure above is a walker whose initial position is x equals 0. The step size g is a random number in the interval -1, 1. To get the next position of the walker, we simply generate g and add it to the current position. To get the distribution of x from this walk, we can divide the domain into discrete locations or bins and count how often the walker visits each bin. Each time it visits a bin, the frequency for that bin goes up by 1. Over many iterations, we get a frequency distribution of x. For example, e of x is equal to x squared, f of x e raised to the x squared, which is very annoying to integrate. Sure. Yeah, that's fair. I accept that. Okay, so what I'll say here is one good graphic, but I'm going to have a few comments on the graphic really quick. Right, so with the graphic, could you create, I'm not sure how it's created. Create a palette first. So it doesn't have the, see, if you look at it really closely, you might not be able to see it on stream, but the quality is not super high. It's fine. The colors, oh no, what did I do? Did not mean to do that. Oh no, I lost everything. Let's see, the colors, every time. The colors are a bit clearer. Okay, and then the other thing I want to mention is because it's a GIF, the issue we had with GIFs before in the algorithm archive is that people didn't like that they auto-played. And so would it be possible? So the other thing too is because it's a GIF, you have to specifically wait for it to finish. Oh, there are MP4 files. Okay. So let's just swap it out for an MP4 file. I'm just going to mention that. And use something like, here, I'll give you the actual command that we use for the rest of the algorithm archive stuff. It would be here, cd projects, see your contents, Gaussian elimination, ls here, vi Gaussian elimination, and let's look for MP4. Here, something like this. Yeah, that'll do. Okay, enter, paste. I don't know what just happened. Okay, well, let's try that again. Up here, and grab it again, and paste. There we go. Add a review comment. Let's keep going. Okay, I think the graphic's fine. So the only other thing I'd say maybe with the graphic is that, again, because it's a GIF and you have to wait for it to finish, having like the end state would be quite nice. Let me see where it actually finishes. So we do the random walk. We bin it. The step size g is a random number in the interval. Oh, I see what you're doing, right. And then we bin it. I'm wondering if maybe we should just have the final image available. Just so it's I think it's fine. I'm being too picky. Over many iterations, we get a frequency distribution of x, right? So random walk with an acceptance criterion. So the Metropolis algorithm works in a similar way to the random walk, but differs crucially in one way. Does the random walk need to be capitalized? Probably. I don't think it does. I think we probably don't want the random walk to be capitalized. I'm just going to put this on the big review here and just say, I think random walk. In the text body. All right. Let's keep going. Okay. But differs crucially in one way. After choosing a random step for the walker, a decision is made about whether to accept or reject the step based on the function f of x. To understand how this works, let's call x of t the position before the step and x prime the position after it, okay? After we define the probability of accepting the step to be a is going to be the minimum value of f of x prime over x of t. So x is before the step, x prime is after, and then 1. So the minimum value, okay, so we have, min of this function. The min function above implies that a is equal to 1 if f of x prime is greater than f of xt, which means that the move will always be accepted if it is towards a higher probability position. Yeah, this is nice. Otherwise, it will be accepted with the probability f of x over x raised to the t. If we create a histogram of this walk, for some arbitrary target function p of x, we can see from the figure below that the frequency starts to look very much like it after many iterations. Yeah, it's nice. It's good. Same thing with the graphic as above. It's just, if you're using FFmpeg, use, thanks for that. I'll fix that. Text body. Okay, and same with the other figure. Again, just use a, same as with the other figure. Same as with the other figure, it would be nice to use an MP4 file. And let's see. An MP4 file and what else? And a palette. All right, that should do. Okay. Yeah, it's quite nice. I like that figure. Okay, so an algorithm for one-dimensional example. Was a color palette. So what you can do with FFmpeg is palette is, I think this will show it to you. It's essentially a set of colors that that FFmpeg knows to use. It just makes the output slightly higher quality. And so if you look at the visualizations here, what's happening is there's it's super hard to show on stream, but you can see it if you look at the PR. There's a little bit of little white dots in the middle of these blue boxes and stuff. And I think adding a palette will fix that. It might not, but I think that fixes that. Specifically with GIFs, I think it'll fix that. But probably the MP4 file is fine. So it's just a way to make the output slightly higher quality. And again, you literally just create the palette by doing ffmpeg eyes input.mp4 vf palette gen. So you just read in all of the images, and then after doing that, you then just use the filter complex palette use, and so this will just force you to use the palette. And you can kind of see in these images here, it's again maybe hard to see on stream, but you just get a higher quality output. That's all it does. It's something a lot of people don't know about FFmpeg, but it really does help the output a good bit. Okay, so okay, the Metropolis algorithm. Oh, I just read that. Let's keep going. So the initial setup. Let our target distribution be p of x is equal to f of x over the domain from -10 to +10 of f of x, where f of x is the function we know and is given by the following. Okay, the code for defining the function is given below. So we have f of x, and then sure, it looks like we have exp of b1. Sure. Okay, that's fine. Since this is an easy function to integrate, and hence our target distribution px, and hence get our target distribution px directly, we can use it to verify the Metropolis algorithm. The plot of px in the figure below shows 3 different peaks of varying width and height, with some overall overlaps as well. Yep. Next, we define our Walker symmetric step generating function as the random walker example, as in the random walk example, not walker, I think. And again, probably lowercase random walk. Let me just look for walker. I think this one, it should be lowercase random walk instead of random walker. One second. Overall, this is fine. I think it's relatively clear. So let's go here, add a view comment there, and keep going. Okay. So here we have def g. We use a random number in the interval -1 and 1. I'm not a big fan of the def g notation here, in that I don't know what g is, but let me read through the rest and figure out if I understand it later. Finally, we choose the domain of x and the initial point for x naught at xt is equal to t0, chosen randomly from the domain of x. So x min and x max is -10, +10. X naught is NP random uniform. X min, x max. Sure. Okay, that's fine. I still don't know what g is exactly. So use a random number in the interval. Next, we define our Walker set. Let me take a look at the source code. What is g? G just returns. I'm an idiot. That's literally this line. Is a random number between -1. No, it's not. We'll use a random number, as in the random walker example. We'll use a random number between -1 and 1. Why do we even... Wait. I'll ask a question later. Let's read through the rest of it, and then I'll try to figure out this g thing later. So generate the new proposed position x prime is equal to x of t plus g. Sure, fair enough. Now I know what g is for. So notationally, it's just g. That's why we're using g as a function. Fine. Calculate the acceptance probability. A is equal to the minimum of 1 and then x prime over t, similar to before, except reject. Generate a random number u between 0 and 1. If u is less than or equal to a, then we accept and move to the set position, which is going to be x. T plus 1 is equal to x prime. Otherwise, we reject and move. Otherwise, reject, move, and set the new position to current x of t plus 1. Okay, right. Increment t is going to be over to t plus 1. Sure. So you're basically saying the most we can move is... we define our Walker. So the most we can move is 1 step to the left or right, and that's fine. I think maybe explicitly saying that. And just saying this means that the most we can move is between -1 and 1, I think would help a little bit. And then also I want to say, edit, I think an explicit sentence. Oop, sorry. Come on. Also, guys, I do apologize. My energy is a bit low today. I don't know why. Just for some reason, I'm just quite blah, and I've been blah for a bit, and so I apologize if I'm like kind of a bit rambly and all over the place. So I think an explicit sentence saying that this sets. Maybe it is clear. Next, we define the Walker symmetric step generating function. As in the random walk example, I'll use a random number in the interval. Right. The step. Size to be between -1 and 1. I think just saying that, I think is fine. The other thing too is I just realized you used g as a step size before, and so that actually does make it clear. Just because for some reason I couldn't remember what g was, but you had already used g up here. And so linking it back up there would be quite nice. So I remember, g is the step size. I just somehow forgot, even though it was up there. Probably people who are reading it through and not like focusing on review would probably like have gotten that, right off the bat. But for me, for some reason, it just took a second to realize, that's what g was. Fair enough. So as long as you say g is the step size, fine. It clicks, I think. Okay, how to iterate. I think this was actually fine. The code for steps 1 through 3 is below. Def iterate x, f is equal to f, g is equal to g. Sure, that's your function, that's your step size. Now we say perform one full iteration and return to the new position. X proposed is equal to X plus G, sure. And then we say A is equal to the minimum of this X of X, f of X proposed over X, and be random uniform. If U is less than or equal to A, X new is equal to X proposed, sure, this is fine. So the following plot shows the results of running the algorithm for different numbers of iterations n with the same initial position. The histograms are normalized so that they integrate to 1. We can see the convergence towards P of X. Yep, looks good. I quite like this plot, actually. It's quite nice. Same, it's Pizza Friday. Okay, so example code. The following code puts everything together and runs a Metropolis algorithm. Let me just, hello. Okay, remove the hamburger menu so I can see it. Okay. Good, so this guy does name main, and let me just run it locally on my computer. Things to consider: any asymmetric function can be used to generate the step. So far, the function g we used for generating the next step is a random number from the interval -1 to 1. However, this can be any function symmetric about 0 for the above algorithm to work. For example, it can be a number randomly from a list of numbers like -3. Sure. In higher dimensions, the function should be symmetric in all dimensions. In higher dimensions, the function should be symmetric in all directions, such as multidimensional Gaussian function. However, the choice of g can affect how quickly the target distribution is achieved. The optimal choice for g is not trivial. It's not a trivial problem and depends on the nature of the target and what you're interested in. Okay, I might actually got to go driving across town. Have fun driving across town. Good luck with the pizza. I actually think moving this up top to where we define what g is would be quite nice, just to explain why we need a separate function for it instead of just grabbing a uniform distribution, right? And the reason you want a separate function specifically for g is because, hey, it could be something else. It doesn't have to be between -1 and 1. A runaway walker, in the example above, the probability decays very quickly as x goes to infinity, but sometimes the function can flatten out and decay more slowly, so the acceptance probability is always close to 1. This means that we will behave a lot like a random walker in those regions. It may drift away and get lost, so it's a good idea to apply some boundaries beyond f of x, beyond which f of x will simply drop to 0. Okay, so I'll mention a couple things here as well. Let's go here. So I think this is actually an important point. Where are we? Here. I think this entire paragraph should be moved up. Okay, add review comment. And then down here, I actually don't know if I understand what this is saying. Let me reread it again. In the example above, the probability decays very quickly as x goes to infinity, but sometimes the function can flatten out and decay more slowly, so that the acceptance probability is always close to 1. This means that it will behave a lot like a random walker in those regions and may drift away and get lost. So it's a good idea to apply some boundaries beyond f of x. Will simply drop to 0. I think that including this in the random walk section is actually important for me in particular. I think it's nice because my naive question when I was reading this is, why do I need a separate function for g, specifically when like it's just generating a random number between -1 and 1? That was my first question when I came up here, and it's answered later. But it'd be nice if there was just a small comment in here saying that in principle you don't have to. It doesn't have to be the full paragraph, but a small sentence just saying, hey, in principle, G could be more complicated than this, would be quite nice, I think. And then in here, I think actually, I think a good, where are we? Then one other thing I want to say is down here. I don't know if I fully understand. The section, maybe a visualization would help. I think that's what it needs. I think a clear visualization of what a runaway walker would look like, I think would explain that a bit better. Now let's see. The only other thing I would say is, in general, and this isn't a hard rule, but in general, the example code goes kind of at the bottom of the chapter, and so for most of the other chapters, people don't read past that example code. And so even though this is really important, I would try to move this above the example code bit so that people still read it before hopping down to the example code section. In the case that you need some sort of clarifying things to consider after that, I'd put it there. Like, we did this with like for example, convolutions and stuff. We had to explain, hey, these are the plots that you're looking for. This is what you should get. But in this case, I don't think we need to do that. I think everything moving above the example code, I think would be quite nice. So I'm going to mention that as well. Also, okay. Overall, it's good. I'm relatively happy with it. Obviously more citations are nice. Maybe a brief discussion of like where else this is used. Just not like discussion, but just saying, hey, this is used a lot in these areas. It would be nice to link people. Like again, I naively was like, hey, what's the difference between Metropolis and Metropolis Hastings, right? And so saying that, here's actually the clear difference between this algorithm and that algorithm, or saying like, this is actually used a lot in this area would also be quite nice. Like just kind of like a few citations to just show people where it's going. You don't have to like put like a clear description of each one in the chapter, but just to be like, hey, this is where this is actually used. I know, for example, the good old thermal physics by Schroeder, which was my, what I did for thermodynamics back in physics, had a discussion of the Metropolis algorithm. And I think it also talked about where it went and stuff like that. But I think at the very start here, giving a brief example of like, talking a little bit more about like how exactly these probability distributions are used in physics, I think would be quite nice. Wherever that was, it was up here somewhere, because it is used a lot in physics for a bunch of different things, and I have frankly forgotten everything about it, and I would love to relearn exactly what that's useful for. But yeah, overall, I think it's pretty much good to go. Let me run the example code just to make sure it does what it said, and then just these few comments I think are all I have to say. And you don't even have to accept all the comments. It's more like, hey, these are my thoughts as I'm going through it. So I think that I have some ideas of applications like generating an ensemble of particles that follow the Boltzmann distribution. Right, yeah, that's actually, if I remember correctly, I think I did that as one of my first research projects when I was an undergraduate. We were trying to figure out, I think it was like the thermal decay of electrons off of supernova remnant plasmas or something like that. And obviously they follow a Maxwell-Boltzmann, or they're supposed to, but actually they follow more like a Dryvestin distribution. And so the question was, well, if they're actually following more of a Dryvestin distribution, does that mean that our timeline for all supernovas are off and all this kind of stuff? And so we did a Monte Carlo-like approach, but I don't think it was Maxwell-Boltzmann. What did we use? No, we did the Monte Carlo approach as a way to simulate electronic interactions. It wasn't Metropolis Hastings. But, talking about the Boltzmann distribution will get people excited, specifically physicists, because they know the Boltzmann distribution. In fact, maybe that should be the test, recreating a Boltzmann distribution in this way. I don't know. I still think it's good. Like, just for the record, this is not like a criticism of it. I'm trying to think, how to make it more approachable and more engaging for people who are actually going to be using this content. And I know for a fact physicists are probably going to be looking at this and being like, hey, what is this actually useful for? Why is it useful for this thing? 1 second. Let me modify my video capture device really quick. Here and there. Okay, perfect. And good. Okay, so let me run the code. Yeah, this is a super easy chapter to review, I think. I'm relatively happy with it. So let's just move this back over here, and let's just run the code. What did I copy? Oops. CD into projects, algorithm archive, contents, and then we're going to go into, 1 second. What is it? It is, what is the name of the algorithm? Metropolis. Why am I so stupid? Metropolis here, ls there, cd into code, ls, cd into Python, and now we're just going to run Python, metropolis.py just to see what happens. I don't remember what happens. I was going to go with Boltzmann distribution, but I decided to stick with a probability function to make it more general. To be fair, I think that was a good idea to do the probability function to make it more general. I think the example code should probably generate a... maybe like do more than one, like maybe do a test with the Boltzmann distribution or something. I don't know. I think the probability distribution approach, making it more general, I think was actually quite a good call. But I think also maybe mentioning the Boltzmann distribution is an idea. I don't know. Like again, just kind of, I think it's already good enough to be merged, but just things to improve on would be, again, maybe citations for where to go with this, what people use it for, all that kind of stuff. Let me run GNU plot, and let me just plot output.dat. I'm dumb? No, I think I need spaces. Plot output.dat. There we go, perfect. I don't know what I just plotted. Oops. Let me see what the code actually does. Vi metropolis.py. So the code will output an output string. Okay, so what is the output string? It's going to be n join for x and x dat. Okay, so we have x naught is equal to numpy random uniform. Where are we calling the function? So we have iterate. So the output string here, x is going to be iterate, and x.dat is going to be append. So, okay, I'm going to just say a few comments here. Would it be possible? How big is x naught? X naught is n random uniform. So would it be possible to pre-allocate the number of iterations? I think so. So can we pre-allocate this array? Is that okay? Okay, so xdat is append this. So let me take a look at the output file. Output .dat. This looks like it should have plotted just fine. So what was that I got? Via Metropolis? Oh, that's because I need to plot it as a histogram, I'm pretty sure, right? Output, no. How do I plot this? Vi output.dat. Metropolis.py g. Density would be the other way. Okay, so do you have your plotting script on hand? What did you do for it? So maybe I do that. So let me do histogram, GNU plot, and let's see, histogram with GNU plot. I forget how to do this. Isn't it just plot colors using X title values? Nope, not quite. No, I want to bin it. I don't think you can bin it. You know, I might ask for pre-histogram data. pyplot.histogram, I see. Okay. Histogram using GNU plot. Let's see what we have. It's quick, simple, although very hidden. So bin width is going to be width times floor of x over width. Sure, plot data file using bin of bin width. 1.0 smooth frequency with boxes. Let me see what happens if I just run this code. What is width though? Width is going to be right, so bin is going to be equal to the width times the floor. Okay, so they have hist is going to be width floor x. Okay, let's see. Man, okay. Let's create another histogram. Okay, so histograms are even following me here with this stream. By the way, thanks. But a few people are following. Adalex, Midov, Sahu DX, and also Techie Chan. Thank you guys so much for following. Sorry, I haven't been on top of things today. Let's go here. Make a histogram using GNU plot. Let's see what we got. Nope. Let's see, make histograms with GNU plot histogram plot style. Okay. Right. Not quite. Probably that last one was as close as we're going to get. Histograms, GNU plot documentation. Let's see, what do we have here? Set box width, set style data histograms. What happens if I just do this? Is this going to do it? Let's do GNU plot. Let's run this. And then that last one's probably not going to work. So we probably want to change this to output.dat. Using call unexpected. So what was call again? Call was not defined. Okay. All right, here we are trying to figure out histograms again. That's fine. Is there a way you can just create a histogram in Python and output that instead? Is there just like a histogram in Python without using matplotlib? Again, not with matplotlib. NP random plot histogram data. Again, you don't want, can I just use histogram? Okay, without, I don't think so. Hmm. Hmm. Okay, well in that case then let me just see if there's a simple script to do this with GNU plot, and then we'll output that as well. Yeah, so the thing is, I mean, creating histogram goes beyond plotting, so I'm surprised that like the only people that have done it are the ones that have created plots. But that's fine. Let me think then. I mean, I guess we can read in matplotlib. It's just, I didn't want to have to read in a dependency like that, you know? It's kind of annoying to read in a dependency for something you don't need. We can just output the data directly, I guess, and then we can plot that in a plotting script. Perfect. That's what I want. np.histogram. Great. That'll be perfect. The only problem with that, though, is that then people have to implement a histogram method in like C or C++, which is going to be a pain. So maybe the actual solution is to do what you did and output all the data and then have the plotting of that data be the... Yeah, and then we plot the data afterwards. Yeah. There's one other thing that we need to do with the code, and that is to have some sort of, like, I don't know what to call it, but like a fidelity measurement. So we know what the actual analytical function is that we're working with here, right? Where is it? We define it, where's f? F is here. So we defined f, so we know the analytical function. So we should be able to just return like an error, like how far away we are from that analytical function. And so having a test like that would be quite nice. And then we don't have to output the histogram, but now I have to think about how to plot it. So let's see how we plot that. There's probably an easy way to do this in GNU plot. I'm just missing it. The reason I'm doing GNU plot is just because, you know, we said that, you know, all the algorithms have, all languages have access. Well, GNU plot is a separate plotter, right? So it's like, hey, if you can plot it in GNU plot, you can plot it in pretty much any plotter. So that's kind of why we chose to do that one. So GNU plot. Let's see what we got here. Making histogram with GNU plot, and again, we're just going to go through it. Set style data histogram is equivalent to with histogram. You overwrite with boxes. Easiest way to make a plot as histogram here is minimal running script. Set style data histogram. Set style histogram cluster gap 1. Plot cumulus_tab. Let's just see what happens if we try running this. Here I'm running random code on the internet again. I can write a script that doesn't use np.histogram, but rather modifies an existing histogram array based on the values of x. It'll be inefficient though. Right, so that's why I think what you did is correct, just outputting all the data. And I think, let me just run this in GNU plot and see what we can get. Set style data histogram. I also have something to add to the review, coding style problem, but I'll do that afterwards. Yeah, please do that afterwards. In fact, yeah, let me just finish this up. And then I'm basically done over here. I just have some coding comments left. And let's go ahead and plot this guy. And we're going to plot output .dat. And this does not what I was expecting. I really don't know what I just plotted, if I'm being honest. But it definitely wasn't what I thought it was. All right. GNU plot histogram, cluster bar chart. Oh, this is a pain. Splitting the data file, stacked box plot. No, you're just not. We have a bunch of data, and I want to plot that. So, calculating histograms, GNU plotting. This should be it. Okay. So we've been with, in figure 1, you see two different distributions of measured angles. They were both given as one-dimensional data and plotted with a defined macro that's doing the histogram calculation. Okay, right, perfect. This is what I want to see. So we load hist.fct. The macro is defined in an additional file, hist.fct, and loaded with the plotting command. Okay, well that doesn't help me very much, does it? Okay, yeah, that doesn't help me at all. Right. Okay, so it looks like, so how do we do this in C++? That's my question. We want people who are using C or C++ or Fortran or whatever language they're using to be able to plot this. It isn't binned. That's probably the problem. Right. It's not bin data, and so we have to bin the data. Now, binning the data is not hard. we can just iterate through it. And the question is, do we do that on the code side or do that on the plotting side? I mean, right. So the code for is just going to be, the histogram. I mean, it depends on like the size and stuff, but it's just going to be like, histogram of like I or whatever. What is it? It's going to be histogram of the data input of I, and then we want to probably divide by n and then floor that guy. So floor. And that should do it, I think. Let's go here. Floor, I think. Right, of this. And n is the number of bins you have. And then I think what we do then is say for I equals, 1 to n, where n is the number of points you have in data of I. And I think that does it, right? Am I dumb? Let me just double check to make sure I'm not super stupid here. Control D, Julia. I'm sorry I'm doing it, Julia. I just know Julia. Hey, Viking Coder, how are you? I think it's better to do that in the plotting side, no? Because how we bin it, or if we can use some density calculation scheme or not, is not part of the Metropolis algorithm. You're right, but my question is, how do you do this in a plotter? That's my stupid question. I'm sure you can do this in GNU plot relatively easy, turning a histogram. But then I'm doing okay, Viking Coder. Thanks for asking. By the way, like, I don't know. So I don't know if it's been a while since I've seen you on stream, but I know like you've been off and on for years. So I don't know, like, hey, how have you been? I think I've seen you a few streams recently, but I just wanted to acknowledge that, like, yeah, I remember you from like literally 5 years ago or whatever, like, way when I started streaming, like a long time ago. So I just wanted to say, hey, and welcome back, I guess. Sorry, I'm kind of low energy today. I don't know why. I'm just low energy. No, see, I don't want any of that. I just want histograms. Let's go. Could load it in Excel or Google Sheets. Right. Well, I mean, or it's super simple to do on the script end though, right? So, I mean, we literally just do, I'm not regular, but that's because of my job and things. Yeah, that's totally fair. I mean, thanks for stopping by. So let me go ahead and do using delimited files. 1 second. I have to add delimited files first. Okay, then I should be able to just read in the file here, and I think it's literally just what I wrote down. I think it takes 2 seconds. I think. Yeah, I mean, it depends on how we want to do the histogram, but overall, I think it's probably fine. Yeah, give it a second. Yeah, and so how we do that on the how we do that on the plotter side is my only question here. Again, I'm sure we can do it in GNU plot, right? Error bars, column stacked. Yeah, I'm just so out of it. I'm not even able to do this. Okay. Oh, come on, stop it. Okay, here, there. Histogram.org, make a quick histogram in GNU plot using raw data. Here we are. Perfect. Okay. Bin width is equal to 1. Edit this. Bin number is equal to x is the floor of x over bin width, rounded, and then unity is equal to 1. Okay. Yeah, okay, let's just see if this does it. Control D, GNU plot. And then we can just add the script with it, and it should be fine. Okay, so we'll just grab all these guys here, paste, and then the next thing we're doing is plotting it. So plot output.dat here. Rounded, not defined. That is because rounded is not defined here. It is defined. Okay, maybe this just didn't work. Okay, let's do each line individually. So bin width is this. Bin number is this guy. Rounded of x is this guy. unit is equal to 1. And then we plot output.dat, see what that does. Enter. There we go. That's what I wanted to see. Perfect. Okay. So maybe we just include this and just say, this is what we're trying to generate, and that's fine. It's not super hard to do. Let me see if there's a better way to do it. Method 2, we have make a histogram with the area of the bin equal to the count in a bin. So the area under the curve is the number of data. That's all commented out. So maybe we just include this script, and that's what we do. Or just say, you know, an example script of doing this in NuPlot or something. I don't know how to include that. But for other algorithms, we just include how to plot the data in NuPlot. So let's just add that as well. Just to say that's how you do it. I don't think that's too bad. I think it's probably fine. So under the example code, where are we? In here. Here, okay. So maybe just adding something like, here's how, one second. And then there should do. Let's add this in there, and this will be fine. It's not super hard. It's probably a section to add in the plotting chapter rather than, sure, okay, that's fine. We can add that to the plotting chapter. But I mean, even so, let's go here. Okay. I think you're right in saying that we should probably add this to the plotting chapter. Okay. So maybe I add that as an issue. Yeah, let me add that as an issue then. Let's go here, issues, and just say adding histograms to plotting chapter. One second. Feature request. Adding. Okay, histograms in here. One second. Okay, I'll just erase all this. Well, not all of it. I need some of it. Feature request. We want with PR. What was it? Metropolis is going to be this guy. To do this in GNU plot, it is something like this. All right, I'm just gonna add it here, and then I'm, I'll figure it out in just a second. Where is it? Here, plotting there. That'll do. And I'll fix it later. Column numbers, histograms here. Sure. And I'm just gonna paste where this is from. It should be here. Perfect. Okay. Additional context. I don't think we need any additional context, so I think the rest of this can be removed. Perfect. All right, let's go ahead and submit the new issue, and then we're gonna go over here. New chapter. Where are we? Here. No? Where is it? Files changed. Maybe it's this one? Oh, which one was I looking at? Maybe it's down here. One second. Go down to the bottom. Okay. Then in that case, I think this is fine. Yeah, the only thing I'd like to see is an explicit test, I think. Random question, if using matplotlib is bad because it adds a dependency, isn't this effectively just moving the dependency to GNUplot instead? Yeah, I think you're right. I need to add that to the plotting chapter. GNUplot is an external program. We want to let users be free to use their own plotter. Right. It's also technically an external program. You guys are completely right about that. So the reason we have plotting separate is because, one, it does distract from the algorithm in a lot of cases. But two, it's because, we're going to have people implement code in Fortran or C++ or I don't know, LOL code or whatever that doesn't have an appropriate plotting scheme, right? And so if the algorithm is fundamentally reliant on having matplotlib or something loaded, then it doesn't really make that much sense, right? So we have to make sure that the plotting is separate, even though most people are going to write their matplotlib script along with the code. We have to make sure that it's just not written that way in the code examples, so that for other people they don't feel like they need to have the matplotlib in there, this type of stuff. There does seem to be a Python matplotlib code option, for example, in the domain coloring chapter, right? And so, for example, in that chapter, it was different because it's a subsection of the plotting chapter. So all the very visual algorithms do require some sort of plotting. So domain coloring needs that. Then also, if you go to, there's a few other chapters I think like that. Domain coloring, iterated function systems as well. It needs some sort of plotting. It's just, unfortunately, you need some sort of plotting for it. And so I think for this one, I still managed just to use GNU plot with it. But this type of stuff is sub under plotting because of that. In principle, it should be another way around. Probably these should be separated out, and I probably will do that soon. But that's just not how it is right now. Domain coloring here again should have a separate subsection for Python, and so should plotting, I believe. Oh, it does not. Yeah, right. So it is a bit inconsistent. But so the plotting right now is only in GNU plot. It's just an external plotting that we provide. If someone wanted to, put the code up for matplotlib or whatever, they can do that as well. But yeah, adding this in for histograms in the plotting chapter, it should be done. You're completely right. Yes, exactly. That's where it should go. I'm going to add that in myself. It shouldn't be too hard, but I'll do it tomorrow. And then let's go here. And let's just take a look to make sure everything else is good. So code examples, license under MIT license, great. Bibliography, license, images and graphics, text. Yep, that looks good. The images are all there, I think. Looks good to me. Okay, so let's just talk about the code next. Where, Amaris probably has more to say about the Python-ic way of this, but I'm just going to say a few things. The first is that might be nice to pre-allocate this array. Super well. Again, I'll let other people talk about the Python here. Add a review here, but it's just it seems like an obvious thing to do. And the next thing is down here, somewhere in here. It'd be nice to have some sort of test. To show that we are generating the right number. Generating something similar to generating the correct function. Okay, perfect. An example of the tests that we've done already. What's a good algorithm to look at for this? We just put out, we have the Barnsley firm, but I don't think there was a really good test for that because it's visual. I just did some tests a second ago. What was I doing for tests? What was it? Approximate counting algorithm, maybe? Probably like the approximate counting algorithm. Should the test be in the example code? Yeah, I think it should be. The example code is like everything there. So for example, in the approximate counting algorithm, here. Correct function, and example test can be found in the approximate counting algorithm. And I'll just paste it here. I think this and that, and paste it there. Sure, there. Okay, that seems good to me. And then once we have the test in there and a few other things, I'll finish my review up here, saying, up here I'll say overall, happy. I think the quality is good. I have a few lingering remarks that I didn't completely mention. That I didn't mention yet. So let's just go and go through. There's one. I think random walk should not be capitalized in the text body. 2, what I want to say is it would be nice to talk briefly about how this is used in practice. I know it's used a lot in various physical applications, so maybe pointing to those with citations would be nice. I don't think there's any need to change the code. I like that the code is for a general PDF, but maybe mentioning Maxwell Boltzmann. Just Boltzmann. That's what you said. No, you said Maxwellian. Which one were we talking about? It wasn't Maxwell Boltzmann. No, it was the Boltzmann distribution. Which distribution were we talking about earlier? I swear it was Maxwell Boltzmann. Wasn't it? Yeah, okay. Would make... One second. Physics folk. Happy. Okay, overall, I think I commented everything else. So let me just double check just to make sure. I mean, again, some of these may not be completely relevant. Like, for example, this one, making a subchapter of Monte Carlo. I don't actually know if that's a good idea or not, but it's something I mentioned. You can argue on that one. I think it's fine to add NumPy. I'm just going to mention that here. I'll actually mention that in the main chat because that was where that was commented. Cancel there. I mean, I might ask a little bit about why we have f of x without allowing us to modify a, b, all this kind of stuff in here. Maybe have default arguments or something so you can change the distribution at will. I don't know. I mean, overall, it's just a function at x that you're reading in, a function of x that you're reading in, so it's not so big of a deal. And again, this is also just an example function to run with. Maybe commenting that would be nice, but overall, I think it's pretty clear. Keep going. Right. Okay, finish the review. Submit review. I probably should have requested changes. It's fine. It doesn't matter. The only other thing I'm going to say is in the main conversation here in saying that for the NumPy argument, I think it's fine in this case as someone coming from an HPC background. I genuinely thought everyone, the first thing everyone did, oh, is it just Boltzmann? What's the difference between Boltzmann and Maxwell Boltzmann? I thought they were the same. Are they actually different? Oh, okay. Let me check Boltzmann. Oh no, that's me being an idiot. Oh, okay. Yeah, okay. There you go. Anyway, you know what I meant. Just pretend I know what I'm talking about, please. My bad. I genuinely thought the first thing everyone did. Everyone did. To import NumPy. I think we should be cognizant and maybe remove NumPy from. Is Maxwell Boltzmann just Boltzmann squared? There was something like that. No, that's not right. I don't remember any of this. I'm so sorry. I have completely forgotten all my distributions. For NumPy, I think it's fine in this case. As someone coming from an HPC background, I genuinely thought the first thing everyone did when using Python was to import NumPy. I think we should be cognizant of the fact that this isn't true for everyone. That this is not true for everyone from less numerical methods. You know what I mean? There we go. That should work. I think that's pretty clear. Okay, why am I not able to comment this? Comment. Okay, why can't I comment this? Am I dumb? Did I do something stupid? Why can't I comment? Let me... I think I remember that we decided that the libs we allowed for Python were only std, lib, and numpy. That sounds right, but I don't remember. Let me refresh the page. Is there a specific reason why I can't comment? Oh, now I can. Okay, sure. Comment now. Yeah, but I think there is a point there, right? Like, I never thought of NumPy as something that people didn't have. I always thought it was like everyone just by default loads NumPy. I didn't think of it, but I think most people are right. Like, I'm sorry. I think that this person might be right in that most people probably just use the math library, right? It's probably only people who are very specifically focused on numerical recipes that use NumPy. I don't know. It's something I hadn't considered. So that's good. Okay, I'm actually going to close it here for today's stream. I know it's been a short stream. I'm kind of like knee deep in papers trying to figure some stuff out. So I'm going to get back to that. I'm going to try to stream tomorrow, hopefully with some really cool new stuff for you guys. Yeah, we'll see how that goes. Thanks again, guys, for coming in. And yeah, I'll see you next time. NumPy is not stdlib. To be fair, okay, yeah, maybe we could use math.random. Yeah, so I'm not sure what the actual solution is there. If you think it's easy just to switch to math.random, feel free to do so. NumPy is not stdlib because the development goes way too fast for the core developers. Okay, that's probably fair. Okay, but that is it for today, guys. Thanks for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And I'll see you guys around next time for the next episode of Leos Labs. Hopefully it'll be tomorrow. Hopefully I'll have just a little bit more energy than I did today. I don't know what the deal is, but I'm just super tired right now. And I will see you guys then. Bye, guys.